Good morning. I'd like to thank you for coming and welcome you to the Capitalist Symposium Grand Challenge 4 on transdisciplinary technologies for better decision-making and data analysis, enabling discovery and innovation. First I'd like to thank the AV team and Lucas and everybody getting this ready and all the people behind the scene making this possible. It's a very exciting opportunity to bring everybody across campus together, and a lot goes into these things. So I just want to shout out to those folks for that. So today we have 4 speakers and 5 people, so 3 speakers and 5 people will be on the panel. So I'll start with a few introductions and then we'll follow with 3 speakers and go from there. So my name is Duane Burleson. I've started here in August. I came over from NYU, and previously I'd been at ASU. And I had, my core areas are human-computer interaction and learning sciences. I have been involved in, so the positions that I took here are as research director for the School of Information and the associate director for the School of Information with a joint appointment in the health sciences, where we're starting a health science design thinking strategy. So thinking largely about how to use these kind of complex data systems across diverse domains. So in that program in particular, and in both the School of Information and in health science design, we're very much about the collaborative transdisciplinary appreciation of expertise and collaboration. And so the title of my talk at the beginning here is Technologies for Participatory Collaboration. So within the human-computer interaction and the learning sciences, we're very much about reaching out and getting the expert opinions of the end users in that process. So I want to have that be a bit of a theme here, or one of many. Each of the speakers will have their own themes and emphasis, and I think that's one of the beauties of this process, is how do we appreciate that broad spectrum, pulling these things together, and ultimately, as Jeffrey was saying, build the kind of environment where we can work across cultures, across domains, and have the kind of futures that we want to have. Just to contextualize the picture here for a second, across the different experiences throughout my career thinking about learning technologies and collaboration, this image is an image that we used to propose to the National Science Foundation to build a holodeck. So some of you may recall or understand that the holodeck was made famous in the Star Trek series, in which it was a room in one or more individuals could go into, and it would become a virtual experience that was also physical, tactile, and multi-person. And so that room could be used for entertainment, it could be used for complex problem solving, it could be used in a variety of different ways. So this picture, we told the NSF that we could start to use a number of different sensors, either in the environment or on the persons, to do a type of team science collaboration, both co-located and distributed, that has not been possible before. So we have planetaria, we have decision theaters, we have reality decks. These are all instruments across the nation that are being used for some of these types of things. But we were pushing forward. Caves is a popular one. Some of you may know Cave 1, Cave 2. Those are products that can be purchased. They're rear-projected, 6-sided rooms. So you're sitting inside a virtual reality environment and you can look in different directions. What we said with the holodeck was that we could fuse across emerging and existing technologies that are becoming increasingly low cost to create a kind of collaboration across both individuals but also entities, agents, robots, and collaborative virtual observatories or instruments at a distance. So here you see a representation of a social robot collaborating with a biochemist to conceptualize a strand of DNA, perhaps a synthetic life form. You have a remote musician here on the right, your left, my right, looking at the xylophonic properties of the bass pairs that are being put in. And so I just want to throw that out there as kind of the embracing or an instantiation of the kind of transdisciplinary collaborations that are possible, unexpected. So already, here in the past couple months, looking at collaborations across linguistics and how some of these can be instantiated in very contextual settings, and you can understand the physiology of comfort or trust between interpersonal individuals, either co-located or at a distance. But also, we've done a series of concerts on the holodeck. So looking at how individuals from, currently in the past, we've done it at NYU, Norway, and Argentina in March with the Turn Up Festival in collaboration with music. Fox School of Music will be doing collaborative distance performance where we're going to have singers and performers in different locations doing this work together. So that's the picture. It'll iterate. I'm not sure the clicker's working. Maybe I'll just click on the keyboard here. So sometimes the technologies don't work, and that's one of the big processes of the technology, trying to get all of these things to work at the same time, and how to fail softly. So that's an important piece of decision making is, are there backups? Are there strategies? Even if I can't advance my slides, can I finish my talk? These kinds of systems. But these are the core areas of the innovation that we're looking at today. So creating environments that can support better decision makings, embracing public values, and scientific information. And so, there's very large debates about what we believe today, in public media, what is truth, what are opinions, and how do we integrate those? So creating environments that can embrace, the multiple perspectives and build continuity. Particularly, one of the things is boundary objects. So these environments can be boundary environments. They can be game-based. They can be reality-based. And then those boundary objects become environments where you can speak about the values and meaning that are embedded in them. Interdisciplinary mixed method, data-driven evaluation to foster innovation in the built environment. So, several of the sentences I've said to date, or in the past 5 minutes, have spoken to this, the mixed methods, the data-driven evaluation. And for the built environment, a few of my slides will look at smart home environments and collaborative teams and how the built environment affect those teams. Evidence-based governance, so with the rich data sets and these environments, that's in part what we're looking at. Through a series of precursor to the holodeck instantiation, some of which I'll talk about, and then in the holodeck itself, you have an environment that can start to use evidence-based. And then across the speakers today, I think you'll see many other contexts and data sets and types of decisions that can be made with these and their impact at all levels of the built environment, both things that are inside, the humans, the buildings themselves, and then the infrastructure and larger scale planning across the kinds of relationships that we want to have, not only with the built environment, but the environment, and what's the relationship of our impact on that. These also speak to the last two, so evidence-based governance and leveraging big data analysis. So one just anecdote, I had the opportunity to apply for the White House Fellows Program and was selected as a regional finalist, and I was looking at how to learn, because I was coming from human-computer interaction and the learning sciences, about policy and some of the implications. And I was speaking with a policy professor and saying, what I'm reading here about the ways the decision-making for the healthcare is, it's largely based on a few papers coming out of upstate New York and Massachusetts, and, and it's unclear if it extrapolates. It feels very much like you just come to these decisions with your own bias, like a liberal bias or conservative bias, and that's, essentially the decision that you want to believe. And the person I was speaking with was a policy professor at CMU. He said, yeah, we know, that seatbelt saves lives, that wearing them helps, but we don't know a lot about what copay to charge people. We could charge free, we could charge 5, we could charge 10 or 50 or couple hundred, right? And so these are the kinds of questions that, across domains, we want to better understand how to apply these and what types of decisions can be made. And so those are the kinds of environments that Decision Theater at ASU and now the holodeck are starting to provide. So I've spoken a lot about this one, but this is a picture of the Decision Theater. It's as you can see, a room that could probably fit most of us in a tight context. You can put a lot of information around the walls and do deliberations. They understand things like flight path planning, height of buildings, water resources, and then more significant ones, or maybe not more significant ones, but extreme ones, like how would you evacuate Greater Phoenix from the pandemic flu? And so you look at these kinds of different environments. We had the privilege of using this environment to build an astronaut robot mission simulator in collaboration with the Jet Propulsion Lab and MIT. And so we had the Apollo lunar landing site here, and we had 50 individuals looking at large-scale decision-making and collaboration across all the data sets that they could possibly find and feed into this environment. So this was a transdisciplinary class that occurred for multiple semesters and was supported by the Jet Propulsion Lab. We also had NASA assets both in the Jet Propulsion Lab and in the high deserts of Arizona with astronauts looking and living in this kind of lunar rover and making decisions about where they should travel across this path. So if the human goes in one direction and the robot goes in another, what are the relative safety levels? And then the key question for a mission is, both a safe mission, but the optimal return of scientific data. So is the expense and effort worth it? And so is that better facilitated by a robotic entity? How is it informed about what we know about the environment? So you're using all of these rich informations presented in these diverse ways to make rich, informed decisions. And so in this context, you can look at the kind of advanced visualization in the upper right, as well as gaming environments. And so if you were to simulate the surface of Mars with water on it, these might be the places that you might find life and want to explore. If you use the strengths and power of emerging gaming systems and collaborative decision-making in those environments, you can start to look at rich contextualized situations and resource allocations in diverse environments. One of the courses that was taught at ASU at the time was policy in World of Warcraft. So if you manipulate some of the currency values or the privileges that different characters have, how does that actually change? And what can you learn about kind of the philosophy of law and the nature of game theory and game systems? Another context for this is analog environments. So with extreme environments such as stations under the ocean or analog systems like the astronaut robot mission simulator, we've advanced a habitat that individuals can be safer and have longer duration experiences in these environments. So that's a type of environment that, that can facilitate decision making. In terms of the learning sciences, we're looking at how can individuals use their physical built environment, like this room, to train themselves and learn how to take care of people in critical conditions. We've looked at what affordances of that room can be translated into the virtual environment. So do you need to build those rich physical environments, or can you facilitate some of them in a distributed context? So here you see some of the similar environments with the similar equipment and decisions that are needed to be made in a gaming environment. Importantly, in the lower left here, you see the physical haptic interaction. So we do believe in all of the history of the human body as an animal and as an embodied creature that needs the affordances. So we still want to have the ability to push on something, the chest of a person during CPR. And so with this physical device, they were able to learn just as well in the virtual environments. So these are big questions about what kind of environments. And even further out, you're looking at how does a team of individuals like a university facilitate a grand challenge like responses to Ebola. And so one of the concerns in the 2014 timeframe when I first started at NYU and joined the College of Nursing there was the Ebola crisis that was emerging at that time. USAID was doing open source collaborations with OpenIDEO, and IDEO was creating contests for the best reaction, societal reactions, innovations. But there was a concern that even if you won a contest, had a great idea, that there was a big gap from an idea to an implementation. And then a place like a university has some of the rich sociocultural and institutional capacities that can work across, say, nursing, engineering, in partnership with a nonprofit like OpenIDEO, in partnership with a government like USAID, and have campuses in Ghana or parts of the world in which these contexts happen. And so looking at kind of an infrastructure from the end user, a transdisciplinary infrastructure that can attend to either the pandemic flu evacuation of Phoenix and the decision theater or this kind of environment. Again, here at ASU, we have Aztec built in. So Aztec is the Arizona Simulation Technology and Education Center built in the Health Science Innovation Building. And they can do everything from bringing somebody in on a helicopter or simulated helicopter with flight nurses all the way to initial triage and then into robotic, even robotic surgical environments. With Barbara Bryson introducing me to Zubin Zhang. Zubin Zhang is an atmospheric scientist looking at particulate matter and nanoparticles in various contexts of the atmosphere. We've been thinking about how does an event like Katrina or wildfires in California or Arizona impact the kinds of decisions that need to be made in this clinical environment? And can you create a large stage theater leveraging Jennifer Barton's Bio5 closed loop sensing lab, leveraging the holodeck, leveraging the Aztec Center to kind of start to advance these kinds of large scale decision making environments. So no one of us has any of the answers, if you will, and even if we did, those aren't necessarily the best answers to implement, and it takes a big gap to implement them. So by thinking about the various instruments that we have, ranging from Biosphere to Aztec to the underwater habitats to the holodeck to closed-loop sensor labs and many of the great resources that U of A has, we have the opportunity to collaborate not only within our own organizations, and particularly led by Kaplan in this instance, with external organizations, partners across the country and the world, both in academics and in industry. And so all of those voices are important. So with that brief introduction, is meant to be expansive. We want to move forward with the speakers today, and I'd like to invite Brian Mayer to come and present his work on resilience in the built environment. So I don't think that's Chris. So we need to bring Brian's, which is.
All right, I can use the keypad. Hi, good morning, folks. Thank you again for patience and being here on reading day, which I like to call, oh crap, I'm going to get a grade at the end of this day and I want to complain about it. No laughs, okay. Sorry, you can tell this morning I've been in my desk fielding student complaints. So I'm happy to be here to talk a little bit about my own research and how I thought it would connect to this panel and thinking about data and data that we might use to inform decision-making and innovation related to the built environment. I am an environmental sociologist, which means that I study the relationship between societies and their environment and the inverse of the effect of environment on societies. And in particular, I study communities at risk. I am a disaster researcher, so I tend to find myself in places where the built environment has been severely disrupted, and maybe in the last 10 or so years have been playing with this idea of resilience as it's grown in very significant prominence, both in research and policy applications, and really been trying to focus on how can we build really high-quality data sets that tackles a social phenomenon in a way that can be very difficult to quantify. So what I thought I would do today was give you a 50-year history of the social study of disaster in about 8 minutes. So let's see if I get there. Okay, so February 26th, 1972, an earthen dam in West Virginia that had been put there by the Pittman coal mining company fails. Water cascades down the Buffalo Creek Valley, causing one of the worst man-made floods in U.S. history. Maybe up until 5-10 years ago, where we started to see really significant disasters related to climate change, such as the Paradise Fire in California, this was considered to be one of the worst disasters in history. 125 people died. Thousands of homes were destroyed. And this sort of was one of the touchstones to say, all right, what went wrong and how can we do better? From a social science perspective, we were fortunate to have one of our sort of leading environmental social scientists, a guy named Kai Erickson, who was at Yale University at the time, was invited by the law firm handling the complaints from the victims of the Buffalo Creek flood to come in and try and document what that loss would be. That lawsuit actually never was finally settled, didn't go to a jury. It was settled out of court for about $13 million. So that's probably what, $30–40 million in today's dollars. But for 125 deaths and thousands of homes, as well as other community buildings destroyed, it wasn't a lot. And so Erickson was invited to go out and do hundreds of interviews with victims of the flood. And one of the things he observed was there was something greater than the primary trauma, right? Of course, we could document loss. We could say how many homes were destroyed, put a dollar sign to that, start to look at deaths and morbidity and mortality, and start to say, okay, here's how we can quantify that loss. But in Erickson's book, which was an award-winning book called Everything in Its Path, he observed what he ended up calling a secondary trauma. And it was this phenomenon that, in my mind, has really become sort of the cornerstone of what we'll call social or community resilience. And so Erickson, in talking to folks, was able to observe that there was something lost beyond just sort of those immediate economic costs. So I wanted to read a quote from one of his interviews. This is a woman and her husband that lost their home. And she says, "Buffalo Creek was more like a family. We had a sort of understanding. If someone was away, then we sort of looked after each other's property. We didn't do a lot of visiting, but we had a general understanding with each other. If we cooked something, we would exchange dishes. It was a sort of close-knit type of thing. Before the disaster, our neighbors, we would look out and tell when one another needed help, or when one was sick or something was disturbing that person. We could tell from the lights. If the light was on late at night, we knew something unusual was going on, and we would go over." So what Erickson came back and wrote in his book, and has kind of, again, sort of become that cornerstone of community resilience, was that light, right? How do we compensate people for a loss of being able to see that light? One of the things that was unique after the Buffalo Creek disaster was that FEMA and others came in and rebuilt a good chunk of these towns. And yet, even then, long after the disaster had passed, Erickson would go back and talk to people, and they would miss things like that light. Not that they necessarily interacted with those neighbors, but that they knew that there was a collective loss, a collective trauma in sort of that disruption of solidarity. So back when Erickson's writing this book, which was published in '76, he didn't have those tools that we would sort of refer to as social ecological resilience or social capital or social networks. But really what he was talking about was there is something lost beyond just sort of the immediate accounting of the disaster. Fast forward then 30–40 years, we start to have more models for trying to estimate what is this concept of what it takes for communities to bounce back from a trauma, from a flood, from a fire, so on and so forth. There are a variety of ways that we can account for this. I wanted to talk very briefly about three that I thought were relevant for this event. And the first one is engineering. So engineering is definitely one of the lead fields talking about the question of resilience, right? Especially from a design question, and is really sort of thought about the rate of time at which a system, a building, even a community can bounce back from some trauma. So essentially, if we're using the ball and the basin metaphor, which is sort of a common way to talk about this question of resilience, from an engineering perspective, it's really about returning to an equilibrium state. What does it take for this system, this thing, to return from that permutation back to the bottom of that basin? And we can really account for that in terms of questions of time. So we can stress a system and then wait for it to return back to that status quo and come up with some type of scale of that time to say some systems are more or less resilient based on that idea of returning back to an equilibrium. Other disciplines have gone a little bit further, I would argue, than sort of the equilibrium state hypothesis, especially in very contemporary circles discussing resilience, especially combining not just sort of built environment engineering systems, but trying to combine ecological services, environmental measures, and then we'll get to community measures in a second, are thinking, well, perhaps it's not just the case that that ball stays in that single basin, right? That eventually there is going to be a crisis, an event that pushes beyond sort of that time scale that that ball can stay within that basin, up and over a threshold and into a new equilibrium state. This, of course, draws on some of the work of Halling and then later his contemporaries in thinking about ecological resilience. But rather than just thinking about time as our primary measure there, how long does it take to get back to that equilibrium? Now we're starting to talk about the magnitude of that stressor. What does it take to push us up and beyond that equilibrium state or that capacity to absorb a shock, but then to adapt and reach a new state? And one can sort of use the language of ecology. Halling was talking about sort of meadows and what it would take for that meadow to reach a new ecological state. Maybe a forest is intruding, a forest is moving back, so on and so forth. But now we're not just talking about time, but again, it's about magnitude. And then there's sort of social resilience, or what I like to call community resilience. Sometimes those two terms are used interchangeably, sometimes not, where we really don't have a very good metaphor for that ball in the basin to say, how does community resilience work? Because in terms of a theoretical perspective, it's really been about, well, it's really about communities' ability to adapt and to learn from those stressors and try and influence what are those threshold states, either to make them higher or lower, in the anticipation of change. So when we're thinking about trying to measure community resilience, we get sort of these harder to think about concepts like adaptation, learning, redundancy, things like that, that don't quite have the same qualities that are easily captured in massive data sets that are publicly available to us, because we're trying to get at something a little bit deeper than what's the cost of the buildings destroyed in the Buffalo Creek disaster? How long did it take to get people back into new homes? How long did it take for the school systems to come back up? But are people still missing that light next door? And how do we measure that? And how do we sort of try and get at what are sort of the community effects for this broader question of resilience? Lots of people are trying to get at this. There are a plethora of measures, various indices, relying on hundreds of different indicators that we think contributes to this very broad concept of social or community resilience. I thought I would share 4 here that are fairly commonly available. I have access to some of these. Most of us can get them. They're sort of publicly available online in some cases. Otherwise, you can cook the recipes yourself. And I highlighted where I thought they sort of touched on this question of the built environment. And what we'll see is there are some commonalities. There are some very, very common concepts that social measures of resilience like to talk about. And those include housing stock. A community is considered to be more resilient if the housing stock is new. Communities are considered to be more resilient if there are building codes that put tighter roofs on homes in hurricane-prone areas. Then we move into other concepts such as transportation networks, communication networks, so on and so forth. But still, a lot of these, so we will just go down the line, I'll introduce them quickly. The baseline resilience indicators for communities comes out of Susan Cutter's, a geographer shop at the University of South Carolina. She very famously developed a social vulnerability index that takes into account a lot of social characteristics, things that we think produce inequalities and vulnerabilities in society, percentage below the poverty line, percentage old, percentage young, percentage minority, so on and so forth. And we tend to cook these things at the county level, where most of these data exist, and say county is therefore high or low on this question of vulnerability. They've done the same thing then. A lot of inversion occurs here in thinking about what makes a particular area more resilient. But in this case, we are trying to take into account things like shelter capacity, medical capacity based on the number of hospital beds available per capita, evacuation routes, schools, so on and so forth. Another measure getting a lot of traction right now is the Rockefeller Foundation has a very sort of prominent 100 Resilient Cities initiative going on. And so part of that Rockefeller initiative was to come up with a way of measuring what makes those cities resilient. So they have what's called the City Resilience Framework. It's pretty much the same thing as the baseline measure, but actually goes into maybe some more kind of techie things. So communication networks, thinking about the ability to communicate after a disaster, which we saw was a major problem in cases like Hurricane Sandy, for example, which has been a big influence on the Rockefeller Foundation. So are people able to communicate both with each other? Are they able to call 911 and get medical care should they need that? And how can we sort of rank the hardness as well as the adaptability of those communication systems? And that should also be part of how we talk about resilience. NOAA has been really active in this, especially when it comes to hurricane vulnerability, obviously. So they have their own coastal resilience index. And there it does a really good job of including measures of critical infrastructure. So there it wants to know how far above sea level is your wastewater treatment plant, how far above sea level are your hospitals, and so on and so forth. So this asks local county disaster agencies to come up with these measures and do a lot of tabletop organizing to come up with a decision-making system and practice that one might be able to respond in the future should a disaster, in this case mostly a hurricane, occur. But here they're doing a really good job of trying to measure some more of those physical properties. And also widely available and sometimes integrated into some of these is the FEMA HAZUS model, which essentially through some data sharing requests have to be approved, but more or less we can get access to a value assigned to every building at the county level. And so if we're sort of thinking about what is the vulnerability to an earthquake in Southern California or fires in Northern California or hurricanes or floods on the coast, the FEMA HAZUS model can essentially give us those measures in terms of a national inventory of buildings and also lifeline systems, critical infrastructure such as transportation, utilities, and hazardous materials or disposal facilities. But in terms of summing all of these things that are available to us, if we wanted to start modeling resilience in the built environment, relying on these secondary data sources, we're once again trapped in that sort of that very kind of physical accounting of what could be damaged in the event of disaster. And it still doesn't really tell us a lot about how individuals, victims or otherwise, would make use of that built environment to try and recover and potentially adapt into the future. So I thought I would finish with another case study that I'm currently working on and try and bring into context some of those data sets and how they could either help or be lacking in terms of what my team is trying to do into the future. So I've been pretty fortunate to work on disasters. That's not what I mean to say. Right? This is the problem of disaster research. You have to be like, gosh, like when's the next big one going to hit? And I'm going to go right away. That's awful. It's unethical. I don't advocate for that. But I have been asked to be involved in a number of disasters: the BP oil spill, Hurricane Sandy, a couple since, and now trying to sort of think about the impact of some of the more recent hurricanes. So we have a team of researchers at the University of Maryland and Florida right now that have been on the ground in the Virgin Islands after sort of Hurricane Irma hit in 2017. There was widespread damage and disruption of sort of core transportation systems. St. Thomas's only hospital was essentially taken completely offline, and the 911 system simply failed to work for about a week's worth of time. Fortunately, there weren't any deaths directly associated with Hurricane Irma, but we've seen a very significant spike in mortality rates in some things that are really strange. In particular, deaths related to Alzheimer's, deaths related to diabetes, and there's a couple more have really gone up in alarming rates. And so the obvious answer is, well, those folks simply couldn't get to the hospital. They couldn't get to their doctor in the weeks and months following Hurricane Irma. But at the same time, there are a number of conditions like Alzheimer's that hypothetically shouldn't need sort of immediate doctoring, right? It really shouldn't be based on seeing a doctor in that week to prevent a death. So that team of researchers has been on the ground trying to sort of document what's going on. And one of our hypotheses is it's the lack of community. A lot of people either saw folks move away, they lacked the ability then to take the street and go over a couple blocks and see their friends. They lost the ability to go to the community center. So we've been trying to figure out a way that we can document what we're calling the loss of social capital in relationship to the built environment that may sort of be a moderating effect on some of these mortality rates. Our challenge, however, is how do we account for that? How do we measure across a rather small island damage to the built environment? Well, we can use a number of these indicators. Some of these use 5-year averages from census data, so they're not relevant to sort of think about damage within a year or even within a couple months. We can use the FEMA HAZUS model to try and say, okay, can we account for financial losses due to damage to those buildings and try and come up with block-by-block measures of what was the financial loss due to damage to the built environment. But we're also trying to go past that. We're trying to say if people are sort of active participants in their built environment, using and redefining how things are used, how can we measure that? Are those satellite imagery measured over time, looking for changes in access to certain key public spaces in the Virgin Islands, particularly in St. Thomas? Can we give people some virtual mapping or online mapping technology and ask us to tell them where they used to go and look for disruptions in that? These things for sociologists and epidemiologists are impossible. We don't have a holodeck. We don't even know what a holodeck is. Could we make use of a holodeck in terms of asking people to think about their built environments? Let's do this, right? That's innovation. And so that's what I've been really inspired by in terms of the workshops that this has taken place. And today's event is, you know, I can come up with sort of my existing toolkit. I've shared some of those ideas here. And if I want to be the next Erickson, sort of writing on what's happened in terms of these places, what are those sort of deeper disruptions of this idea in community and then resilience, the ability of these communities to restore and come back and adapt, how can we actually do a better job of measuring the built environment? I don't know what that answer is, but I'm trying to get there, and I'm looking forward to interacting with some of you in doing so. So thank you for the time.
Great, thank you, Brian. Now we will hear from Chris Castro and his work on weather systems and rich data sets that help in thinking about decision making. Chris? There you go. Great. You'd already done it. Yeah. Okay.
Just advance it on the computer. Okay. So I'm going to talk about high-resolution weather and climate modeling to inform decision making. So a little bit about where I'm from. We are the Department of Hydrology and Atmospheric Sciences. And so this was a merger of two departments that took place a couple of years ago. And I think it's really good in terms of our merger that we're really reflecting that we need the integration of disciplines to address these types of problems that I think are now part of the University of Arizona strategy. So, so our vision for the merger was to create a department that could better study the integrated atmosphere, land, water cycle. And this is just a cartoon that illustrates that we're talking everything from precipitation processes, clouds, and then land surface processes, and like evaporation and runoff, and then even the groundwater properties. So this involves a lot of physically based measurement and modeling, increasingly at high resolution. So just to emphasize where we are, we're in this frame of better decision making and data analytics, and I've just listed the priorities again for your reference. And we really do best fit within this priority in the built environment strategy. And so what are we talking about? this is an example for the use of forecast from weather forecast timescales out to climate projection timescales, and you see the forecast timescale on the y-axis. So a variety of practical uses for this type of information: emergency management, aviation, agriculture, energy, water resources. So I'm going to touch on a few specific examples to Arizona and the Southwest in my presentation. So a primer for those of you that don't know how the weather works here in Arizona, we have 2 wet seasons. You're in one of them right now. So the cool winter storm season, dry spring and foresummer, and then we have the monsoon. So cool season precipitation is dominated by winter storms, large-scale winter storms that covering the entire size of our region. These are important because they deposit snow in our mountains. That's a source of water for our reservoirs. And if you live in Arizona, you need to be very concerned about what goes on in the Colorado River Basin. This is our primary water supply and for 40 million people. This is managed largely by the Bureau of Reclamation, and what is very important for water supply is the melting of snowpack from the upper basin that you see here in the map. This is a real big concern if climate change is going to negatively impact water resources in the Colorado Basin. Arizona is in a very bad position because by the Colorado River Compact we have junior rights. And just aside of climate change, that water resources can vary substantially in relation to natural climate variability. So here you see the time series of Lake Mead water level from the 30s to the present, and these are wide swings so the critical point from a manager decision standpoint is the lake going to get low enough that you have to make some sort of decision that is going to affect water supplies that go to the legal bounds of the Colorado River Compact. Then for the monsoon, this is our severe weather season. The scale of precipitation is different, so we're talking small scale thunderstorms that the concern is more extremes. And this is really centered more in our part of Arizona, in central to southern Arizona, and also in New Mexico. So monsoon is predominantly a severe weather hazard. So you're talking about dust storms, flash floods, microbursts, lightning. So just to summarize, for the decisions we need to make here in relation to our weather and climate, it's a cool season snowpack streamflow issue that governs the water supply, and then the warm season thunderstorms and heat that is our water demand and also a source of natural hazard. So just some methodological approaches that we use to improve forecasts and projections. So the starting point for all climate change projections, for example, from the Intergovernmental Panel on Climate Change that you may be familiar with, are global climate models. But the rub is that these are inadequate for regional and local impacts. So we have to do something to create higher spatial and temporal resolution information that better represents hydroclimate, that can then go to that step of the impacts translation step. So we have 2 routes to do this. One is statistical, to develop an empirically based models and then apply that to future projection. The other, which is more what I do, is applying a full physics regional climate model over a specific domain of interest at a higher resolution. So this is really a question of quantity versus quality. Statistical downscaling is very relatively simple and inexpensive, easy to apply. But dynamical is better, that it represents physical processes, and it can better characterize extremes, which is more what we want in a changing world. The big advantage of using dynamical downscaling is it better accounts for the non-stationarity problem. The problem with statistics is it's only as good as the data that you train it on. And so we are exploring more this dynamical downscaling because it gives us more of a physical process basis for assessing future change. And so if your emphasis is more the physical process uncertainty, this is the way you want to go. And when you think about like monsoon thunderstorms, extreme precipitation, this is a big motivation. But to get there, it requires the use of high-resolution modeling. And what do I mean by high-resolution modeling? I mean modeling at the kilometer scale. This, in the parlance of atmospheric sciences, is referred to as cloud resolving modeling, because we are able to explicitly resolve the storm scale structure. So you think squall lines and outflow boundaries of thunderstorms. And we already do this here at the U of A for purposes of weather forecasting. So we run quasi-operational weather forecasts in our department that are provided to a variety of stakeholder entities in Arizona. And this is just a sample output from one of those, from a weather forecast simulation that might indicate, for example, on this day, that we're going to experience heavy rainfall in the Tucson area, that then we need to make some management decisions on how we deal with that. So there's a sausage-making process necessarily for weather and climate model information that then goes to supporting decisions and impacts assessment. You got to have data hardware. So when I mean data hardware, this is high-performance supercomputing resources. Also the infrastructure to collect data. I've shown an example of NASA satellite products there. There's a plethora, emerging plethora of new observation-based data, especially in the remote sensing realm, that we take advantage of. Then you need community-based modeling. You generate more confidence by the generation of more multi-model ensembles that can better characterize uncertainty. But that is a large exercise, and it takes resources of multiple institutions and federal government laboratories. And just example, if you want to do regional modeling, for example, that is done in this Cortex project, as I'm illustrating here, for all of these regions in the world, that is a global effort across institutions across all the world. Then you need customized data analysis and visualization. So you need common repositories to hold code, so the GitHub environment, and then you need common ways that you can visualize data. For example, the MetPy software. And then after all of that, that's just the science part. Then the physical science part. Then you have to have the information translation step, which is often overlooked. But this is really important because this is the sustained interface between scientists and the stakeholder decision makers to foster the co-production of knowledge. You got to establish a framework for communication and information dissemination. And above all, this process builds trust and confidence. There's an element of human psychology here. You're not going to deal with someone that is just giving you data. You have to iterate with them. You have to trust them in the information that they're giving you. And this is essential in any process where we want to connect the physical science-based information and weather, climate, hydrology to the policy-making and governance aspects. So some specific highlighted project examples that I've worked on. So we've looked at simulating extreme monsoon precipitation events using the cloud resolving modeling approach. So we take climate change projections from IPCC-based models. We use a dynamical downscaling approach to simulate the severe weather events down to kilometer scale, so in an event-based approach. So similar to the paradigm of a numerical weather prediction forecast. And then we can look at those simulations at the kilometer scale at things like changes in extreme precipitation, and then compare that with available data, for example, from gridded station observations. And what we find, this was one of our most cited papers in the last few years, is that we have an increase in extreme precipitation centered, but now we're getting geographically pretty specific about where that increase in extreme precipitation is. Specifically, we found it's in western Arizona, southwestern Arizona. Well, why? And that is due because that is where it doesn't rain very often, but when it does, it is the most intense organized type of convection in what we call a mesoscale convective system. This has really profound implications for the infrastructure out there. So you're talking like the big solar generating facility. We have DoD facilities that are located, and DoD was in fact the agency that helped sponsor this research. And then we work with reclamation. So I'm borrowing a couple slides from Lindsay Barrett from the Technical Service Center in Denver that is from an ongoing project to look at water resources in the lower Santa Cruz Basin. So very much in the spirit of the information translation, this has been an ongoing process over several years where a scientific team has met in public meetings to develop the scientific approach and then the information translation. So this is a lot of moving parts. So to take future climate scenarios and then how these are defined is informed by the stakeholder interaction. Then validating those data and then putting those into a hydrologic modeling tool that then decision makers are already familiar with, that then we can put in the context of here's what you're already familiar with to make your operational decisions. Now here is what, in this paradigm, what the future climate change projection will be for things like stream flow and groundwater. And this is just an example of an emerging output from the project, I think is a very provocative result. So this is looking at the scale of the lower Santa Cruz River Basin, future projected spatial stream flow for what we're defining as best and worst case climate scenarios based on the choices of models that are stakeholder informed by our iterative process. And what you see here is in the case of the worst case scenario, that is the dynamically downscaled model that we provided them to generate their streamflow projections. You see fractional changes in streamflow of that are pretty significant, 20–40%. This has real potentially significant implications for decision making at the local and regional scale. And now to change to a different part of the world. So this summer I was in Saudi Arabia because we had a new project there. And they're very interested in using convective permitting modeling to how they can forecast extreme precipitation events several weeks out. And why is that important? You think of Saudi Arabia, it's like Arizona, pretty dry, but yeah, they get extreme precipitation events there too. And their cities, and you're talking cities of millions of people, very important places in the world, they're very infrastructurally ill-equipped to deal with these types of things. And so it's the same kind of meteorological phenomena that we have here in Arizona, this organized convective events. So what we're developing for them is a capability with new sources of data that are historical reforecasts over periods of 20 years. Can we mine this data and use high-resolution modeling to see if over a 20-year period, is there skill in forecasting these extreme precipitation events several weeks out. And these are preliminary results, but these are for forecasts 1 week, 2 weeks, 3 weeks out from an event. And what we find is for this particular precipitation event, we're getting the location of where the precipitation is occurring in the forecast almost 3 weeks out. This is very encouraging. If we can develop this, this can provide a great source of information for this very important realm of decision making at what we call the subseasonal forecast timescale, several weeks out, where you have to make a lot of critical management decisions. So, some concluding thoughts. I think the real challenge here is how do we marry data analysis to decision making. So the data analysis requires a high level of technical capability and coordination, complex models, high performance computing, sophisticated post-processing analysis that is inclusive of artificial intelligence, AI techniques, and visualization. As a professional, this inherently requires a large amount of time to keep up with the rapid technological advances, even within one's own discipline. And also, from an infrastructural standpoint, where you're conducting this research or how you want to do this enterprise, it requires substantial investment. You can't get around that. So it takes a lot of time and it takes a lot of money. But then you need this decision-making part. Requires building trust, communicating scientific knowledge, new ways of thinking, co-production of knowledge. Well, that also requires a lot of time. And to the point, it has to involve necessarily an intermediate professional or organizational entity that has this specific expertise in the science, information, translation, and public policy. I would say we are in a fortunate position. The University of Arizona does this latter element really well. And I think the example of the Lower Santa Cruz Basin project that I presented is really a great illustration that we do it well. And all involved have to commit to working together. We have to hold hands in an iterative process to get the optimal results, or it won't work. So that's all I have to say.
Thank you, Chris. Yeah, great. So I think we're starting to see how these different parts are fitting together and the need for the gap building, bridging, the kinds of environments that we're talking about, the kinds of data sets, the institutional capacities can all bring together. So our next speaker is Aletheia, and she'll be speaking about how these types of data can help us understand how to build environmentally and design environmentally sound buildings and make appropriate decisions in these complex contexts. So looking forward to the next presentation. Thanks.
Thank you so much for the introduction. Yes, I'm Aletheia. I am an assistant professor in the School of Architecture. And I have, my background is as an architect, and I also have a doctorate in architectural sciences with an emphasis in built ecologies. So today I'm going to be speaking a little bit about a different mode of decision-making with data. And the decision-making that I will be framing is really addressing the designer's process. So when I say designer, I'm speaking about those who are responsible for conceiving of and establishing the conditions for our built environment. So that might be architects, engineers, and others. So rather than looking at the modality of integration of data for policy decision-making processes, this is more of a kind of a bottom-up approach from the design standpoint. So I also will be addressing some slightly different range of scales. So moving from the regional context into the building scale or the urban scale to the building scale, all the way down to how we might be thinking about collecting data and information at the material scale and nano and micro scale conditions. And I think one of the major gaps in our built environment design processes right now is finding ways to really link these interscales of data with different tools and techniques and methods. Part of that clearly is related to our need for connections in interdisciplinary activities, but part of it is also residing in the development of new tools and techniques to accomplish that integration. Also, in a different way of thinking about data, of what we had just seen in the prior presentation, looking at very long timescales, long-term data sets, and looking at the change in climate data over centuries or decades. For our work, we're really interested in the timescale within the annual time frame, and then the sort of seasonal differentials and even the diurnal differentials. So for buildings and built environment conditions where we conceive of the relationship to human activities, human thermal comfort, energy flows, water flows, all of these kind of patterns of environmental integration in built environment have a very dynamic condition on a both seasonal and diurnal way. And so for us to see these dynamic data sets at that level of resolution is really beneficial for us to think about new ways of addressing our built environment and our buildings and our building technologies and our civil engineering systems for adaptation. So we might be thinking about adaptation in that sort of predictive modality that has been mentioned prior, but we also might be thinking about just the need to reconceive and reconceptualize our material conditions, our spatial conditions for adaptivity, in this case, in response to climate data. So we look at a resolution of an hourly basis, and there's 8,760 hours in a year. So we're working with that many data points typically in most of our design processes for buildings. We also consider the spatio-temporal conditions. So clearly the sun has a very unique geometric position in relationship to any given building site or built environment condition or location or region in the world. And that has a lot of implications on our access to daylight, our access to solar energy, and of course the impact on energy consumption and energy use within our buildings. We also think about the human and the social condition in relationship to these environmental flows. So when we look at the integration of the environmental data, we're also considering what are the social patterns of potential use, whether it's a programmatic scale between different buildings in a district or a city, or whether it's within a space of a given building and the differential use of that space from season or from day to night. And we begin to make correlations with the data and the information that we have in a very visual way. So you're starting to see here some representation of heating loads and cooling loads within a spatial plan. So we're kind of looking on the right there at we might say a typical floor plan of a square floor plate building. And we have different thermal zones within the building. And we begin to identify intensities through data analysis via simulation tools that are integrating our climate data and our building information data. And we can then visualize what is happening with our thermal flows in zones within a building or within a city. And we can definitely see, like, even in some cases, we will have heating loads, heating demand in one area and cooling demand in another at any given hour or time. And we can begin to kind of use these tools and techniques and visualization processes to also think about the material systems with which will be most effective or beneficial for energy conservation or human conditions. So just looking at the multiplicities in a comparative framework with different programs or different material conditions. We also think about the integration of this environmental data to inform the morphology of our buildings. So we might be thinking about just the autonomous building on a site as an architect and engineer, but we'll also study that in relationship to the broader urban scale and urban condition. This example is integrating the solar mapping and solar radiation within our building facades. We might be looking at airflow conditions as well, whether that's for structural design or whether that's for wind load conditions or for natural ventilation and passive cooling. To kind of bring that back to Arizona here, some of my specific research emphasizes innovations in building technologies that are responsive to our extreme kind of conditions in our climate and in our region. So, for example, how do we respond to abundant sun, volatile water conditions, unique plants, and the unique biotic communities that we have throughout Arizona, even the potentials through nocturnal energy and extreme heat conditions. So I'll just give an example of the development of a project that integrates data analytics in another kind of new way of thinking in the design process. And this is a solar-induced water evaporative advanced technology. It's SWET. It's like a little evaporative cooling wall, but it also allows for natural daylight to pass through from the outside of a building to the inside, while it allows for a kind of natural cooling process. And you see these are conceived in modules because part of our interest in the built environment and building design is to think of distributed flows and distributed conditions, and the potential for adaptation is where we can begin to break down the scale of kind of what we historically have established as large-scale, centralized, static conditions. We're starting to see in reference to biotic adaptive systems that we can also develop that in our own physical constructions. And that is to say that we might have kind of modular conditions that are able to respond to localized data and adapt, whether that's environmentally or to a human. There is a test bed that is established for integrating data sensing and actuation response. This is an environmental test bed. It's conceived of having a building technology kind of put in the center, and we have two volumetric conditions on either side of the test bed with which we can have inputs and data collection outputs. And the entire framework is linked to simulation tools that allow us to integrate machine learning processes so we can begin to run data sets through simulation and then also link the data that is emerging from the physical prototype back into the platform for what we're calling a methodology for machine learning integration with model predictive prior reinforcement learning. And that's a special technique or kind of theory in the machine learning realm where we have a kind of online physical test bed, and we also have the simulation producing data and feeding back to the physical system to allow it to evolve, in a sense, and respond differently to data that's being received through the platform. So we did some initial tests with this, just using an electropolymeric film that just responds to electric charge, and we had a dimmer system on some halogen lights, which are obviously outputting quite a bit of heat as well as light, and just kind of asking the system, can it begin to respond in one way or another, becoming more opaque or more transparent to different photometric sensing data conditions. And this is showing how that data is taken back into the building scale simulation platform to basically inform the energy performance and the surface temperature exchange that would be occurring on building enclosure systems should we be using that particular material system, though there might be others. The other area that we're looking at with the integration of the data and a lot of like sensing data collection techniques is with the human and bioresponsive material systems. In particular, we're really seeing a great potential for a new mode of having our material systems in the built environment be capable of responding to human conditions in the very local space that we might share with our material systems. And that is to say that currently our buildings have these large centrally mechanical cooling and heating systems. And so this entire theater, for example, might have a lot of cooling energy running all the time, even though there's hardly very many people occupying it consistently. So could we begin to think about energy conservation and human needs on a more localized scale and responsive kind of scale and system? And that in part would also address a great diversity of human demographic and physiological need. We also integrate the data in simulations and physical prototypes to inform other environmental benefits, such as water conservation potentials, using a lot of different data analytic techniques. And ultimately, I think, as I had mentioned in the beginning, there's a great need to really begin to think around the relationship at different scales. Whether we're potentially collecting sensing data about emerging contaminants in our water systems, or about pathogens in our microbiome in the indoor environment. How can we sense that information and feed it back into system scale and building scale and urban scale analysis engines to allow us to adapt? And more we are seeing a lot of sensors integrated within buildings. Many practices now are using buildings as a kind of research tool themselves to allow us to learn more about that. I'll leave it there. Thank you.
Great. I'd like to invite our speakers back up to the stage, and I'd like to open the floor for questions from the audience for our speakers. So while they're walking up here, please prepare yourselves. Anybody have an initial question? Yes. Kristina. I'll add to the challenge. If we can keep the answers relatively brief, then we get a more series of questions. So.
I'm thinking. So
yeah, that's a tough question. So I guess my very brief answer to that is the problem I face when I kind of reach that interface is you have to know in the what I call the decision maker stakeholder, you have to know what they're thinking, what their priorities are. Then from the data perspective, that sort of tools your analysis to fit their frame of thinking. So in the Lower Santa Cruz Basin project I presented was a really good example. We started out not knowing how were we going to characterize climate change projections in a way that was going to be useful for their decision making. To figure out the paradigm of how to do the work was literally a year-long process of iteration.
Yeah, and I think, I mean, from my standpoint in my discipline, we see the social data as in two different modes. I mean, one, we kind of see a structuralist approach where we're looking at the collective and what's significant for collective human needs and human systems, but we also see from a phenomenological standpoint of the individual and what's the kind of individual human need, and there's actually data there that's also very relevant, and being sure that we don't ignore one or the other in any of our design thinking processes. So I think that can become a blind spot if we're only looking at collective data. We might just have kind of quantitative results and lose some of the qualitative potential.
I think I would follow on that and say, so I was helping NOAA come up with that coastal resilience indicator, but they really only use it for very local decision making and sort of tabletop exercises in terms of how do we build local capacity. And inherent in that is sort of the phenomenological belief that we either should or cannot compare what New Orleans is thinking to Mobile, Alabama, because there's a lot of local context and sort of idiosyncrasies. Now, of course, not everyone agrees with that, and then they sort of try and scale up from there, but we really start to lose high-quality data, and we sort of say a county is resilient. A county is a huge place, and so, to me, the answer to your question is really sort of instrumental in terms of where are we using the data to do what, and if we can identify that, then I think we can answer some of those questions, but there's a lot of range right now in terms of where we're making those decisions and using the data. So it's almost impossible to answer, I think, from my perspective.
I would respond saying that I think that it's exciting to see the different perspectives and how, and particularly I think Aletheia in one of the final slides about the integrative framework, and if we can expand that integrative framework to not only include the dimensions across the data, sort of technical pieces of the data, but the socio-technical pieces and then the fully social pieces. I think one of the best ways to do this is to do the end-user participatory collaborative design that I think each of the speakers have spoken to, but I think as an institution, we need to take that several steps further. I think that if we can enhance transdisciplinary collaboration and access and pathways across communities so that end users are actually facilitated by the direct access to these data sets and tools for their own appropriation and their own purposes, then we get a much richer understanding of the capacities that we need to have in society across these domains and others. So, let's reach out to some other questions as well. Yeah, so I mean, maybe I'll ask each of you to react to each other's presentation or anything that's been said so far, and just to think about the ways that you might be thinking about your own work slightly differently in the immediate context, or that potential collaborations might come out of this in one direction or another.
Another hard question, thank you. I mean, I think the diversity of perspectives here was, I think, some of the largest of panels that I've been on. So it's an interesting question to be asked. I mean, to me, scale, right? We heard about micro, we heard about regional, you had maps of global, and here I am talking about valleys and communities and counties, and that becomes a question of, how do you integrate that, especially as sort of the decision making. So I was thinking about the communities that I'm working in and saying, okay, here are these various indices of resilience. We can look at them and then identify where you might fall short and then come up with a sort of collaborative plan to improve that. I've never thought about micro and materials. Maybe I should. Could I get a focus group to be thinking about building materials? Maybe. Can I get them to sort of be thinking about 2 to 3 weeks out into the future in terms of regional weather patterns? Maybe, but I am not in my current work. So I think that's a challenge that I'd love to figure out how to tackle, and I think that's sort of what's bouncing around in my head right now, scale.
Yeah, I would agree with that. And I think especially, I presented a lot of work that is going to how will our world here in the Southwest be in the future. That has implications for the infrastructural design and how do we revolutionize our thinking for materials and construction. I think that's the connection. And so eventually we have to get talking across our communities in terms of how does this inform infrastructural design, and then how does it inform the social response to climate change, down to, like, is there going to be a psychological response?
Yeah, I agree entirely. And I think, yeah, I mean, you saw the examples of the climate data that we integrate in design processes, and we do use some models that are actually looking at future-oriented data sets, right, with the predictive modeling tools. But myself, in my own work, I actually have some work down in post-Harvey disaster relief situation, and part of it is that I'm really interested in the sort of post-analytical condition of structures and material systems in a disaster condition, how we can learn to do things differently based on a response to that. And there, I saw a lot of FEMA workers out in the east end of Houston, in communities that there were a lot of post-flood problematic health conditions on the indoor environments, and nobody could be relocated, and it becomes very problematic. And so this is a kind of question of, I think we do need to be doing things differently, in all these areas. How much is data going to help us, and how much are other methods and techniques going to be needed to allow us to kind of, I think, adapt over time with all those situations.
Yeah, I'll answer the question that I asked a little bit, which is, I mean, I'm glad we're recording this because I think there's an opportunity to go back and think about the key points and how potentially like a position paper or some kind of context to synthesize some of what we've said and put some structure behind it with respect to what some of those opportunities are to maybe take those next steps over the timeframes that we can imagine those occurring. So, I can see, at various levels that opportunity emerging. Great. Yes, another question. Great. I'll just try and recap the question, and then so looking at the diversity that we have presented and the transdisciplinarity in each of our work, is there advice on how members of the audience or anyone can take the next steps in their own perspective of creating those transdisciplinary interactions. And do we have any advice or tips in that respect?
Money helps. You know, I consider myself to, you know, want to be, and I like to think I'm practicing interdisciplinary work, but at the end of the day, I belong to a disciplinary department where I have teaching, instructional, mentoring, as well as research responsibilities that I have to sort of meet. And there's not a lot of credit for interdisciplinary work, right? I don't get sort of a star on my annual evaluations if I collaborated with someone outside of my discipline. It'd be nice to get a raise, or, you know what I mean? So that's not there. And so sometimes the question is, what does it take to get us out of our disciplines? And oftentimes that's very individually motivated. I think I sort of get the sense, I haven't had an opportunity to interact with my co-panelists, but I get the sense that they want to think past their disciplines and sort of think about the larger problem. And either that comes from a very sort of personal route, or they're sort of finding a way to make that work. And so what I've been impressed with sort of the RESTRUCT initiative is that there are some seed grant opportunities to develop transdisciplinary teams to say, this is something that we believe in as an institution. We are going to help bring you out of your silos and create opportunities to do that. And sometimes it takes a little bit of incentive to get us out of that, to say, all right, it's worth X percentage of my time that could otherwise be spent within my discipline. And so I think what's happening right here in this room and across this initiative is great. And other things that I've participated in at this institution, whether or not it's the Institute for the Environment or other programs, haven't quite taken that tact. And I'm really hopeful for what's happening here.
I echo money helps. But also it's time and money, and that's what I emphasized at the end of my presentation. And in some ways, people's time is more valuable than money because it's how they prioritize things. Because when you want to really develop a synergistic idea that is going to go from like core scientific data to social outcomes, you have to get a very diverse group of people in the room. And they all have to be committed in terms of their time to be there. And they all have to be unified and persistent through a long process to get to a desired outcome. And so you have to allow for an element of this relationship building and trust. So I return back to my point. There's a psychological element here of how do you break down barriers and build new communities with people that maybe haven't traditionally worked together before. And that's a social process. There's no way around that. And the most important thing, yes, money is important to facilitate it, but people's time to commit to be there.
Yeah, I think a big part of seeding any kind of interdisciplinary frontier is a really good research question that calls for that. So, for example, Ernst Haeckel was a biologist in the 19th century, and in the 1850s, when he was observing, we might say, the kind of anastylosis of nature and the degradation of biological habitat, he was documenting that, and then he started to ask questions why. And he started to see, well, it's not just this insect or this bird that I'm studying, but it's actually the bird's habitat, the bird's food cycle and stream, and he coined the term ecology. And actually, right, it opened up a new discipline as we know it, and it was because he started to have those questions about those connections that nobody had really dug deep on before. So I think it really starts with research question and then finding the people who might be able to bring the answers together.
Great. Well, it is close and time to conclude. I'd like to add a small point. I think it's kind of the motivation. If you're intrinsically motivated, if you can think of that within yourself and are open to the transdisciplinary collaboration, even if one or more, it's kind of the knocking on cold calling. Don't be shut down because somebody's not accessible. Somebody else will be. Also, if you think of toolkits, toolkits are methods for democratizing innovation. So you can take sticky knowledge from individual domains through toolkits which are mentored by ambassadors, like the data science fellows, for example, that then allow end users who don't have core expertise to do things and apply those tools to their domains. So, if we can think about our research and our infrastructure and institution as a series of toolkits and potential and, to ask and answer these kinds of amazing, intriguing questions that we don't even know are there yet. I'm thinking, do trees make sound when they grow? And these are the kind of like out of the box questions that different institutions on the fringe and then eventually coming into the center are pushing forward the boundaries of what's possible. People when I presented this kind of model for a university, we had undergrads asking, can I make synthetic life? And master students saying, what's the fractal nature of dance? And so if we can live in an environment where we can ask these kind of wild questions and then potentially have the tools and collaborations to build them and go after them, I think we're in a place that we all want to be and have the collective community resources to build the kind of futures that we want to have. So I want to thank everyone. I think there are some updates for lunch, or at least a time frame for lunch, and then there's a series of talks in the afternoon. So I look forward to seeing everyone back, and please speak with us further on any of the topics that you'd like to share with us. Thank you so much. Thank you.